Okay, so this follows along with the blue sheet that you got in class today. This is section 6.2 in your book. It's about exponential growth or decay. Exponential because the variable that we're working with here is t, which is most like x that you're used to. And the big C here in the standard function, y equals ce to the kt, is the initial population. So that's at time 0, how much do you have? The k represents how fast what you have is growing. Okay, and so it's positive when the amount of something that you're measuring is growing. K happens to be negative when the amount that you have is decreasing. So this can be used a lot in like biologies, right? When you're measuring the rate of growth of like disease or bacteria. In chemistry, I think like a lot of carbon dating and radioactive decay is measured and examined using this formula. It kind of branches over into finance and talking about how money grows. So it's got a bunch of different connections to a bunch of different subjects. So it's kind of fun for that reason. So what we're going to do is a series of word problems on here today that go along with it. The first one here is example 1. This is as easy as it gets. This one has no context whatsoever. So this is just bare variables and numbers. So it says the rate of change of y is proportional to y. This statement right here is the key that lets you know, okay, since the rate of growth of whatever it is I'm measuring, y, right, is proportional to how much is there, y, this kind of gives you license to use y equals ce to the kt. We'll talk about more of why that is tomorrow. So they give you some information. They say at time 0, ding, 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 my initial condition is 2, and when time is 2, my y value is 4. And what's the value of y when t equals 3? So there's really two components to this problem, right? The first thing you have to do is establish this equation, which means you have to solve for the c and the k in the equation. And then the other part is then answering the question that's at the end. So it says, what's the value of y when t equals 3? So what I generally do is I take the given information and I make me a little data chart, and I want you to do the same. So on the left side is always going to be the input. Usually it's t. It could be x. You never know. And over here would be the output, or the y. I've seen it be w. I've seen it be s. I've seen it be b. I've seen it be I don't know, maybe S. So you just never know what you're going to run into for the variables. But this is generally the independent side, and this is the dependent variable. So I know these two facts. I know that when t equals 0, y equals 2, and I know that when t equals 2, y equals 4. Okay, and so from this first fact, since this is the initial condition, I know this much information so far, right? The initial condition is 2, right? So I can drop that in right for the c value. Now what I have to do is use the second point to go ahead and figure out what k is. So I'm going to put in the 4 for y and the 2 for the t, and it's going to look like this. Okay, and then what I'm going to do, I'm going to solve this equation for k. So I'm going to divide both sides by 2 to get rid of this guy. And so bringing my work up here, I've got 2 equals e to the 2k. And we learned a lot last chapter, right? To solve this equation, I need to take the natural log of both sides. I'll do that slowly on this one, and then I'll kind of skip this step in the next example. So obviously the ln and the e kind of cancel each other out, so I have natural log of 2 equals 2k. And so again, to solve that, okay, I can just divide by 2. So k is natural log of 2 all over 2. So you can write it this way in its exact form, or you can go ahead and get an approximation for it in your calculator. We can do it either way. Usually it's going to help more often than not to go ahead and store this. So I would take my calculator here, do natural log of 2 divided by 2, and then store that immediately for k. All right, and so then I have that full decimal in there, and I don't have to worry about you know, chopping it off, rounding it, whatever. I have everything that I need to be working with. Okay, so once it's stored in there, I can go ahead and write this. I have y equals 2e. So the portion of k that I am going to put into my thing is, the way that I like to do it is to put 0.346 dot 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 t, which implies there's more to this decimal than is there. So let me zoom in a little bit and see if you can see that. Okay. And then now that I've established this equation, I solve for c, I solve for k. Kind of the first part of this problem is done. Now I have to go in and do the second part. So the second part is answering this question at the end. What is the value of y when t equals 3? So I'm going to go ahead and use this function that I created and solve for y. Okay, so I'm going to kind of just show that this is part 2, section it off there. So I have 2e to the 0.346 and then input the 3. there. And so when I calculate this, right, I'm going to use this stored value. So the way that I get my answer for y is to do 2e, and then I'm going to put up here 3 alpha k. And then that means it's going to use the full decimal that I have here. So this is my evaluation. And so my final answer is y equals 5 point, be accurate to 3 decimals, 6, 5, 6 or 7 would be appropriate. Okay, so this is your final answer here. Okay, so that one's super easy. Okay, we can make it more difficult rather quickly. I'm gonna kind of let you guys do number 2 now on your own. It kind of follows that same process that we did for number 1. There's not much that's different. So I'm going to let you guys do that same thing, set up this. Okay, so you can pause the video and try that now. Okay. And so if you did it correctly, you should get t equals 80,000, 058.467 years. Okay, for your final answer. So work that out and see if you can do that there. If you didn't get that answer, I'm going to guess maybe you had a problem generating the values in your table here. So this time my independent variable is t, my dependent is g. So at time 0, right, I have 10 grams of plutonium in the atmosphere, right? And so now once the 24,100 years go by, since it's the half-life, you get to generate that second point, right, by taking half of 10. So this is a second data point. And so if you didn't get it the first time, try this now. It's going to run just like example 1, and hopefully you can get to this here. Okay, example 3 is the hardest. This is the other kind of population growth and decay that we deal with, right? So in number 3, you'll notice as we read it, and here we're dealing with a population of fruit flies, it's increasing according to the law of exponential growth. Okay, that's the sentence that says, okay, you get to use y equals c e to the kt for this one. Then it says there were 100 flies after the second day of the experiment and 300 flies after the fourth day. Experiment, or approximately how many flies were in the original population. So here and here, that means I'm going to take my time, right, which we'll just call the days that have gone by, and then we'll call P maybe for the population of the fruit flies. So after 2 days, right, there were 100 flies. Okay, and then after 4 days, there were 300 flies. Yikes. And so you'll notice, different from the previous ones, right, my initial condition is not given to me. Up here, right, I had initial condition because I knew at time 0 what my value was. In example 1, I knew at time 0 what my value was. In example 3, I have no time 0, right? That's actually what I'm solving for here. So this is going to be the variable that I'm searching for, the answer that I'm searching for. Okay, so how would you start this off is to kind of do a system. We have to solve for C and K, and I have 2 data points to do that. So I'm going to set up 2 different equations, right? One is going to be, I'm going to put this, so let's think of this way, so you know where I'm going with this. That's a C e to the kt. Okay, so if I use the variables here, T is still time, P stands for population, so that's kind of like my Y value now here. So I'm going to put 100 in for P equal to, I don't know what C is, E, I don't know what K is, but my time that has gone by with that 100, the number of 100 fruit flies has been 2 days. So I'm going to put that 2 in there. Okay, and then what I can do is I can solve this for C. Before I do that, though, let me kind of show you where I'm going next. So the other thing I'm going to do simultaneously, right, is to write another equation just like this using the second data point. So I'm going to do 300 equals C e to the k times 4. Okay. So I use this data point to write this equation. I use this data point to write the second equation. And now I have a system, right? I have 2 equations and I have 2 variables, C and K, and I should be able to solve for them. So I'm going to go ahead and do this by dividing this guy by e to the 2k. Okay, so I have this statement about what C is worth in terms of k, right? Looks like this. I'm going to drop that up in here for this variable C, okay, and then kind of solve for k from there. Let me see here. So I'm going to put this in here. 300 equals 100 over e to the 2k. So that's a straight up substitution for C. And then e to the 4k, like this. Okay, and now I have one equation with the variable k in it. Okay, so I have to do some magic here. So I'm I guess I'll do this really slow this time and then maybe not as slow other times. So I'm going to just group this differently. I'm going to put the e to the 2k over the e to the 4k instead, right? I can do it. It doesn't matter which one it's over because it's in the denominator of the product of both of them. And so I can simplify this down, and I can actually divide both sides by 100, right? So that my new equation, kind of in one fell swoop here, 300 divided by 100 is 3. And then if I simplify this expression, I have e, right? I'm just going to subtract the variables since they have the same base. So 4k minus 2k is 2k. So I have e to the 2k here is what I've kind of whittled this down to. Now I'm going to take the natural log of both sides. So natural log of this side, right, will cancel with this e, and I'll just have 2k left, and then divide by 2. So my exact answer for k is natural log of 3 over 2. And now I'm going to go ahead and work backwards to get this c. Okay, so that's pretty easy, and that's going to be a calculator problem. So I'm going to go ahead and type in, let me make sure the glare's out of the way. I'm going to type in natural log of 3 divided by 2. To get this value, and I'm going to store that for k immediately because that's what I'm going to do often, right? And so I've got that value stored for k, and now if I go back over here, right, and try to evaluate this to get the c value, I'm going to do 100 divided by e, and then I can just type in 2, again, alpha k to get that I need there, okay? So that turns out, oh my goodness, I had 33.3 repeating fruit flies, which you're probably like, how can you have 0.3 of a fruit fly? But I'm thinking, hey, maybe one of those fruit flies was pregnant. I don't know. So there's a third of a fruit fly somehow, somewhere. So it turns out, right, my answer then after I evaluate this, kind of arrows all over the place, you know how I roll, I would have 33.3 repeating fruit flies would be my answer. Because remember, my goal here was to figure out the original population, and that's what that c value represents. Okay, so that's that. Okay, you can try example 4. Example 4 is actually going to be very much like 1 and 2. Okay, your answer for this one, just so that you have that to work towards, is y equals 71,554.175. And then your units on this one are going to be units per month. So see if you can get that. Okay, and then if we flip it over, example 5 I think is pretty similar to the other two. Yes, it's much like example 4. I'm going to kind of set you on your way for example 6 here and talk about how we would set up this particular data table. So here's a problem of something that maybe we're doing in chemistry class, right? It says the rate at which salt dissolves in water is directly proportional to the amount that remains undissolved. So this first sentence, like the other ones, gives us license to use y equals c e to the kt. It says if 10 pounds of salt is placed in the container of water, okay, so that's going to be my initial condition, right? At t equals 0, the amount of salt in the container, I guess maybe you could call that S, that says set, salt, right, is 10 pounds. And then it says 4 pounds dissolves in 20 minutes. So after 20 minutes go by, right, in time, how much salt is left in the container? And this is where you have to be careful with what you're reading, right? It says 4 pounds dissolves, but if my initial condition was 10 pounds of salt in there, you actually have to account for the fact that 10 minus 4 would mean that there are 6 pounds still undissolved, right? Because this amount of 10 was 10 pounds undissolved to start with. So that's the trickiest part of getting through example 6. Okay, and then if we kind of write our question mark statement in here, it says how long will it take for 2 more pounds to dissolve? So this means you're actually solving for t in this problem, right? And so if we want to know how much is undissolved at that time, right, for 2 more pounds to dissolve, that would mean I would do 6 minus that 2 for a total of 4 undissolved pounds. So this one is a little different where you're given the c value up here you can see is 10. You'll have to use the second data point to solve for k. And then from here, right, you can go ahead and put 4 in for y and solve backwards to get t. Okay, so go ahead, pause the video, see if you can figure that out. Okay, and when you come back, the answer you should get for t is 35, hello, what just happened? 35.8748 minutes, right? If you didn't get that, we will discuss tomorrow. Okay, and then you don't have to do example 7 for tomorrow. That's going to kind of be where we jump off together. So everything else on here, example 6, example 5, 4, and 2 should be done, okay, with these 2 problems going over for you and a couple hints about the data tables.